Hi, good morning, guys. It's Mr. Chen again. So today, just want to talk about slope field with differential equations. And again, this one is for calculus BC. And I'm sure a lot of students having tough time with some of the slope field problem and also the differential equations, the way to integrate it. So we'll talk about the differential equation later. So first thing that I would like to go through, it's the slope field. Okay. So slope field, so that means it just graphically display the solution of the differential equations. So let's say that you do have a graph with like a rational functions, so it shows like a derivative of the functions. And when solving the differential equations using the slope field, so it's not necessary for you to solve the equation analytically, so you just have to insert xy value. So basically kind of like using the xy value, so or the xy derivative table, so you can find a derivative for like a specific slope at like a certain point. And the resulting lines represent the slope of the differential equation at certain points on the graph, allows the person to visualize the actual graph of the equation. So it shows like a pattern, like a trend, whatever the way that I like to label it. So we can just figure out the differential equation. So now let's take a look at like some of the example here. So differential equations. So that one is given, it's dy over dx. So this one is given as x plus 2 over y plus 1. So the best way to find out the slope on each specific point, it's about using the xy derivative table. Okay. So try to use those point here. So 0, 0, 1, 0, negative 1, 0. So again, this one is just like an origin, the x, all the x value. Again, it's all the easy number. You don't want to use fractions. I mean, it's up to you. You want to use fractions. It's just like taking for a little bit more time to find out the slope. So just use the easy number. And then once you plug in those numbers back to the differential equation, so we end up with the slope 2, 3, 1, 1, 3 half, 1 half. And as you can see that those point here, okay, so 0, 0, so the slope, and 0, 1. Again, so the slope getting toward the right hand side here, so it looks like it's getting a little bit deeper. So the slope going to the left hand side, so this one tended to be a little bit more flat. So that means, the point that I go to on the right hand side, the deeper the slope is going to be like. And here's another example for the slope field practice. Again, this one is labeled as y squared minus 2 quantity over the quantity of x plus 2. And again, you want to use those easy numbers, so you want to choose 0, 0, 1, comma 0, 2, comma 0. So any spot right here in the corner of those square boxes. So plug in the point, so you guys see that the slope here is negative 1 comma 0, so the slope would be negative 2. Okay, so, and then 0, 0, then that'd be negative 1. So this one is just like opposite of what the graph we just saw previously. So the point I tended to go to the right hand side, so it seems like the slope is getting flat. Okay, so the line segment is getting flat here, so the slope is getting less steeper. Okay. So this one is one of the example we can try. So ratios, well, this one dy over dx, so that equals cosine of x. So you probably want to use radian. So in order to sketch the graph on the calculator, you want to use radian for this. So we do have pi over 6, pi over 4, pi over 3 with all the x-intercept. And then the point is over here, so it's 1 unit higher. Again, using the table or the column, so you end up with all those type of slope. So cosine of negative pi over 2, well, obviously that's considered 0. So the y value, it's like being meaningless for the rate of change, the slope right here. Okay, so just put in all the slope. So at negative pi over 2 is flat, so that means the slope is 0. Negative pi over 3, so it's getting positive. It's getting deeper and deeper, as you can see that going to the origin. And then back from the origin to the right hand side, so this one's getting a little bit less deeper. So eventually, by the time that reached to pi over 2, it's getting flat. So that means the slope is 0. And here's another example you can try. So anytime that you want to find out the differential equation, make sure that you need to isolate that dy over dx first. So isolate this, so we got y to the power of 3 over x squared. Again, putting those numbers, so we get all the slope. And then you just basically just sketch the little line segment for the slope. So now back to the integration review, and this one is the power rule. So anytime they want to integrate the power, x to the power of n dx, so always raise up the power by 1 and then divide it by the new power. But don't forget, make sure that you need to add the constant c. And then derivative, well, of natural log of x is always 1 over x. So the integrals of 1 over x dx, then that would be natural log of absolute value of x. And for those students might be wondering why is always being considered absolute value, because we just want to make sure that x got to be positive. Back to the parent graph of natural log of x is always considered like a logarithmic function. So there's nothing like on the left hand side of the x value, so there's no such negative number there. It's always considered positive. So that's why we just want to make sure that the x value is always positive. So the domain for this one is always from 0 to infinity. So now let's do some practice. So try to integrate all those type of functions. You'll end up with x to the power of 5 over 5 plus 4x plus c. So this one is pretty straightforward. So just use that the power rule integration formula. And then this one, if you see any rational integrand, that means it's considered natural log of that integrand. Okay, natural log of the quantity of the denominator. And don't forget about that constant. So anything that's missing, you want to multiply it, because you want to make up the number. So you multiply by the reciprocals of the number you make up. And then plus c, so that would be the family constant. It's an indefinite integral. So now let's do some rigorous problems. So anytime that you deal with the differential equations, so let's say that you do have a variable, dependent variable, top and the bottom, or the other way around. So the way that to integrate this is by using integration. Well, it's by integration using the separating by the variable. So you need to separate those two variables out. So what we can do here, so this one is considered dy over dx, so equals y over x squared. So what we can do, we can always cross multiply. So once you cross multiply, you'll deal with that 1 over y dy, and then 1 over x squared. So for the left hand side, so the integrals of 1 over y dy, that would be considered natural log of absolute value y. The right hand side, then that would be negative 1 over x plus constant c. And for those you might be wondering, how do we solve for c? Well, for this one, there's no initial condition given, so we're not solving for c yet. So we just want to keep the constant c there all the way through. And then in order to get rid of the natural log, we take the e on both sides. So once you take e to the power of natural log, it's always 1. So we just bring down that y back to the normal position. And then the rest of this, we just want to solve for, well, just simplified it. And then one thing we notice for the properties of exponent, so e to the power of c, so that's just a constant. So this one is just like the basic properties of exponential, the sum, and then so once you combine the power, so we can separate it. So e to the power of negative 1 over x, and then times e to the power of c. So e to the power of c, that's just another random constant, so we just call it another c. So c e to the power of quantity negative 1 over x, and that would be the original equation. Okay, so again, e to the power of c, that's just another arbitrary constant. And then this one is the property that I just applied, so it's something that you learned from Algebra 1. So e to the power of the quantity of x plus c can be separated into e to the power of x times e to the power of c. So we can say that's a sum to product. So that means another constant, we can just use that random constant c there in the front. And one thing you notice, e to the power of 0 is always 1. Okay, so now let's do one of the problems that we do have an initial condition. So here's another example for the integration by separating the variable. So again, so dy over dx, so that's considered x over y, so y dy equals x dx. Integrated both sides, so 1/2 y squared equals 1/2 x squared plus c. And then in order to solve for y, so you multiply everything by 2. So again, once you multiply by 2 with c, you'll get another constant c. You see that the letter c, this one's bigger, so that's another different constant. And then square root both sides, so you got plus minus square root of x squared plus c. And here's another example you can try. So here's the step that you have to go through. Again, separating the variable and then integrate it by using the power rule, and then solve for y in terms of x. Again, c, we don't know what that is. It's just a random constant c. So now, and here's another example, but this one that shows the initial conditions. So once you separate the variable, integrate it, and then natural log, and then take the base e both sides. And one thing that for sure, that natural log of 1, it's always considered 0. Okay, so once you solve for c here, we can just plug in the conditions. So natural log of e, the reason why y equals 1, because that's part of the initial condition value. So once you solve for c, and then you just want to rewrite it. So y equals x times e to the power of 1/5 minus e to the power of negative 1/5. Again, for the natural log here, so once you take the base e both sides, the natural log got canceled. So that's why there's no more natural log remain. And then try to take out the greatest common factor, e to the power of negative 1/5, so we end up with this. So here's another example you can try, x squared over y to the power of 5. So this one is considered like a hyperbolic equation. Again, initial condition. So once you integrate it, you'll end up with 6 root of the quantity. Okay, so check it out, the step-by-step process. Again, it's the end of the period, so it's going to be lunchtime. So let me know any questions, so please put in the comment. If you guys like to watch more videos, so please check it out, the previous one that I post up on YouTube channel. And if you guys do like the channel, I would like to subscribe it. And thank you for watching the video today. Appreciate it.